We are very happy to have our own David Spivak telling us about the free monad, cofree comonad, and topological space associated to a polynomial.
Okay, great. Thank you. Thanks, guys, for coming. So, to any polynomial functor, which I'll define again, in case you don't know or haven't seen it, we can associate a monad from set to set, the free monad, and it has a nice description that looks kind of like syntax trees. This would be like one element of the free monad, and this would be kind of the arity. A co-free comonad, which is like some kind of, well, it's a comonad from set to set. So it's a functor from set to set and some property, some structure on that. And it looks kind of like this. I mean, it's actually infinite trees. This would represent a single infinite tree. And you can kind of maybe move from states to states. And if you get a true, you stay where you are. And if you get a false, you move to this state. And you get a false, you stay there. If you get a true, you think everything's good. But if you get a false, you're dead or something like that. So you could make a state machine. And that will have something to do with the co-free comonad on a certain polynomial. And so I'll talk about those two things. But then what I found interesting was that there's a topological space whose points are turn out to be the co-free comonad applied to 1, which is the terminal co-algebra. You don't have to know what any of these words are. I'll tell you what they are. But you take this co-free comonad and you apply it to the set with one element. And you get the set of trees. And those form the points of a space for which the elements of this thing on 1 form a base of the opens of that same space. And that topological space, when the polynomial is finite, is called a stone space. Those are the same thing as Boolean algebras, op. I'm just going to tell you this whole story and try to start from scratch. And the reason I think it's interesting is that, so there is a claim that's probably too strong, but Poly is the true language of computation. So why is that even an okay thing to even contemplate whether it's a good idea or not? Well, there's dependent types. Dependent types are a way people talk about computation. You can write programs in Idris or something like that using dependent type theory. And so Steve Audi and his student Clive Newstead showed in the Poly workshop and in Clive's thesis and stuff like that dependent type theory has something to do with polynomial monads. And we're going to be talking about polynomial monads, but we'll be talking about free polynomial monads. So there's dependent type theory. There's database theory. And there's, this is really all about C-sets and what are called data migration functors. So being able to turn a graph freely into a reflexive graph, or being able to turn a dynamical system into a graph, or being able to take a simplicial set and then extract the n simplices or whatever. That sort of stuff is database theory. And a third major aspect of computation is just state machines, Turing machines. Oh, sorry, these are the comonoids in Poly. And by the way, we'll be talking about polynomial comonads. And the bicomodules. Now you could say, what are all these fancy words? But like in any category with a monoidal product, monoids, I don't know whether to say monoid and monad, or monoid and monad, or comonad and comonad, but you can talk about the comonoids and the bicomodules, and if you do that in Poly, you get categories and data migration functors. So they're not like, they're words that a category theorist already knows. And so we're just saying, oh, if we do this in Poly, we get dependent type theory, or we get database theory. And state machines, like for example, Turing machines, where you have a processor and you have a tape, and the processor is feeding something to the tape, and the tape is feeding something to the processor, and they're going and doing some stuff. These can be understood as what are called Moore machines or polynomial co-algebras. So you have this category where all three of these things live very naturally, more stuff too, like lenses and initial algebras of endofunctors and W types and all sorts of things. But kind of the reason that it's worth saying this is even like, something you might imagine is because it has like denotative semantics, operational semantics, and like kind of database-y schematic stuff, all in the same world. And so it seems like the kind of place where we can ask, like, how does language, like what I'm saying right now, move like material, like the way your neurons are firing? This is like the question I really kind of want to understand. What's the way that my language right now, even though it's in some syntactic way, I'm using ands and ors maybe, or I'm saying that like this type depends on this type, and I'm saying some stuff in language, how does that affect how material flows through space and catalyze like, large flows of stuff that gets everyone in a room or something like that? Somehow, language moved you into this room. So I want to understand that. And so this is kind of a place where language lives in this monad-y world, polynomial monads. You can write syntax trees. And over here in state machines is a kind of comonad-y world. And it turns out what I think is interesting is that the free monad, which is syntax trees, the cofree comonad, which is kind of like possible fates or experiences like this, form the points and the opens, or basic opens of a topological space. So that's what I'll be talking about. So there are two toposes. A topos is a place where you can do logic. Two toposes associated to any topological space. To any polynomial P. One is p-coalgebras. That's a topos. The topos of all. I'll tell you what a p-coalgebra is in a minute. And another one is like there's a certain stone space, or more generally, if P is not finite, there is a topological space and sheaves on that space. Sheaves on this stone space, or whatever slightly more general thing, is another topos you can assign to P. And so one is more like this is p-coalg, and this one is more like sheaves on the stone space. And so that's what I want to talk to you about today. Okay, so the plan for the talk, I think I'm just going to leave this on the board in case I need to refer to mainly this stuff, is I'll tell you some background about polynomial functors and what one is. I'll tell you what a comonad is, and a co-algebra, and a monad, and an algebra, and the free one, and the co-free one, and all sorts of stuff about those. And then I'll show you that there's a topological space, this one, SP, space associated to P, whose points are the elements of the co-free comonad at 1, and whose basic opens are the elements of the free monad at 1. And then once we have that, I'll talk about these two toposes. Actually, I might have gotten something wrong here. Well, it looks like that's what I'm going to be talking about. And then I'm going to tell you, if there's time, about the monad map that kind of gives you, I don't know if there'll be time to talk about that, but maybe there will be. There's a monad map from the free monad on P to the internal Hom from the free comonad on P to the free monad on P plus 1. And that just kind of internalizes this fact here, like how the basic opens and the points coincide. They coincide through this in some way. Or how does an open include points? It does it in this way, somehow, in a way I might have time to tell you. So any questions about kind of where we're going? Okay, you may have no idea what any of the things I've been saying are, so I'm just going to give you some background. On polynomial functors. So a functor from set to set assigns to every set another set. And one way you could do it is you could send x to the set of functions from A to X. So if you fix a set A, you could send X to this thing, and the number of elements of that is X to the A. So for example, if A is 0, then the set with 0 elements, Homs from that to X is 1. So X to the 0 is 1. And so I'm going to call this thing Y to the A. It sends a set X to X to the power A. So Y to the 0 of anything is 1. Y to the 1 of anything is itself. Y squared of anything is X squared, etc. And a polynomial functor the thing that may, if you believe that dependent type theory, database theory, state machines are what computation is about, this is a very important thing if you agree that computation is important and you agree with that statement. So a polynomial functor is a sum, a coproduct of representables. This is called a representable functor. And so, like you would write, P is a sum of a bunch of representables. So for example, you could have y cubed plus 2y squared plus 4. And that would really be y cubed plus y squared plus 1, y to the 0, 4 times. So what would this sum be over here? It would be the number of summands, 1, 2, 3, 7. So there's 7 summands here. And yet that 7 is exactly, if we take this to be P, then P of 1 is 7. Because if you plug 1 in for y, then you just get the number of summands. And so I'm going to write P of 1 here because P of 1, evaluating P at 1, is the number of summands. So this is just a kind of compact notation that writes any polynomial as a sum of representables. The number of things in that sum is P of 1. This is just a compact notation for things like this. You could also have like list, which is the sum over all natural numbers of y to the n. This would be like 1 plus y squared plus y cubed. And that is a functor from set to set. You plug in any set, you get a set. Okay, so Poly, the objects of Poly are these things. Things you can write like that, and Hom, Poly from one P to another P, is just all natural transformation. Between these two functors. So I have a functor from set to set called P. I have a functor from set to set called Q. And a natural transformation between them is a map of polynomial functors. There are other ways to say what Poly is. I've said it's sums of representables. Another way you could say it is it's the free completely distributive category on one object. There's lots of like really nice ways to say it, but I'm just going to say this. And one thing I want to be able to do is draw pictures. So this thing here, this P, I might draw like this. P has a little corolla with 3 things. It has 2 corollas with 2 things. And it has 4 corollas with 0 things. And that's another way of writing P. And the reason you might like to write P that way is because of how composition looks and where these trees are coming from. So for example, I could have the tree, I could have the polynomial, I could have a polynomial that will generate that thing. So let's say P was plus y squared plus times, so 2y squared plus 0 plus 1, so 2y squared plus 2. And then what is P composed P? P of P, I'm going to write it this way, is P composed P. Plug P into P. Well, what it would be if I took 2y squared plus 2 applied to 2y squared plus 2. That means plug this thing in for y here. So you get 2y squared plus 2 squared plus 2. So I'm plugging this thing in for y. And that thing is equal to 2 times 4 y to the 4th plus 8y squared plus 4 plus 2, and et cetera. So you get 8y to the 4th plus 16y squared plus 6. Yeah, 10. OK, now that thing is going to be annoying to draw, so I probably shouldn't have chosen this one. Let me do a simpler one. So what is y squared plus 1 composed y cubed plus y? That's y to the 6th plus 2y cubed plus y plus 1. And the reason I draw this little triangle is because if we draw y squared plus 1, and then above it we're allowed to draw y cubed plus y, and then what are all the options for that? Well, we could have this one with this one. We could have this one with that. We could have this one with that. We could have this one. What did I do? We could have, right, do you agree? This times this is y to the 4th, not y cubed. Thank you. And then I could have this. And these are all my options. If I want to take these corollas and on top of, like, pick one of these, and then on all the leaves put one of these, then I get these options. And then the answer is I get 6 leaves here, so that's y to the 6th. I get 4 leaves here, 4 leaves here, 2 leaves here, and 0 leaves here. So this triangle symbol means put these on top of these. It's also just composed polynomials. And so back to this guy, one of the things I could have drawn was plus times plus plus. And this would be an element, like we're starting to get close to this sort of thing here. This would be in P compose P. Oh, kind of. Does that make sense? Any questions about these pictures? Composition of polynomials? I'm just plugging one polynomial into another, yeah.
The terms that you're going to get here is, like, you could have substituted in 1 for y here to figure out how many terms you would have gotten.
Yeah.
Yep. And then if you like plug that in for where you're substituting, if you square that like says, yeah, I think like
I can plug in 1 for this, and that's y squared plus 1 applied to 2, because there's 2 things here, and that's 4 plus 1.
Yeah.
Yep.
How much do you care about the names of the elements in the sets?
I need to be able.
Draw that thing in P compose P. You really mean it's in P compose P and not in P compose P evaluated with the sets kind of made anonymous, right?
With the sets made anonymous.
Well,
Yeah, I'm really supposed to. I need to be able to track when I write like 5y. The number 5, I'm really meaning to be like the set 1, 2, 3, 4, 5.
but you're doing more than that in that picture, in that you're also saying, that's a real composite. Like that tree belongs in P compose Q for a pair of polynomials, right? Because it's a 2-layer tree.
Yeah.
Are you kind of just ignoring that?
I think what you might be saying is that like this is not equal here, it's isomorphic.
Right.
That's right, that's a good point. That's a very good point. So this is really isomorphic, and one of these is corresponding to one and one to the other, and yeah. So yeah, and I think this is even slightly wrong. So it is a sum of representables if sum means coproduct. I guess that's right, but it might be like coproducts are only defined up to up to isomorphism. So is a functor. So in some sense, what I wrote is right, but it's also nice to say that it's isomorphic to a sum of representables. Okay, so that's polynomial composition. Another thing I need to tell you about is tensor, I think. Why do I need to tell you about tensor? Do I really need to tell you about tensor? Oh. I'm not really sure I need to. I think I'm going to skip it for time reasons. So that's composition, and I think it's also, I want to say P composed itself n times. In other words, P composed P n times. Like what you would draw is like a P, some element in P of 1. You would write some position here, one of the summands, and then it would branch according to P bracket I. And you probably have forgotten the notation that I said. So you would pick one of these summands, you would label it, and then for every element of P bracket I, the representing set, this thing, you would branch. And then you would draw another element of P bracket 1, P of 1. You'd pick another position, or you'd pick another, like one of these guys. And then you'd branch according to it. Maybe this one is one of these. So you don't branch at all, and then here you branch. And you just keep going, and you get these trees of height n. Okay. And those are going to come up in both the free monad and the co-free comonad. So maybe that's what I'll talk about next. One last thing about polynomials. So the coproduct of polynomials. So polynomials are functors. And they're functors from set to set, and you can ask for the coproduct of two functors. And if you have polynomials p and q, the coproduct is just p plus q. So the notation works very well. Plus is really the coproduct in the category of functors. And the product of polynomials, this is the categorical product. Like you take the, it's got a universal property that it projects to p and it projects to q. So what is the product of two polynomials? It is their usual product as like polynomials from arithmetic. So the nice thing about this notation, or just this category of polynomials, is that all the standard operations on polynomials, composition, plus, times, those mean something categorically. Like plus and times really are the coproduct and product. Okay, so now let's talk about.
A quick question.
Yeah.
What are the morphisms, Wally?
Natural transformations
Between
polynomial functors. So you have two different functors. They assign to every set, like that set squared. So let's say your polynomial functor is data my poly x equals foo xx or bar. That would be y squared plus 1. And if I did Bob's poly here and did another one, it would be a natural transformation between these two functors from my poly x to Bob's poly x. I'm trying to write in Haskell. I don't know if I'm doing a good job. For all x. Does that help?
I'm okay with moving on.
Okay. All right. So, co-algebras, comonoids, algebras, and monoids. And I maybe could say comonads and monads. So p-coalgebras are dynamical systems. What is a p-coalgebra? A p-coalgebra is a pair S comma F, where S is a set, and F takes S to P of S. That's just what a p-coalgebra means. But how do you think of that thing? Think of S as states. And then for every state, so let's say P, example, P is happy, sad, dead. Oops, no. Happy, sad, y to the true, false, plus dead, y to the 0. Then I could have a set S mapping to P of S. For example, I could take the 4-element set mapping to this thing, P of 4. And what I'm going to do is I'm going to send 1, backtick 1. I'm going to send to happy, the happy summand, and true maps to state 1. So see, let me try to read this to you. For every element of 1 through 4, I'm supposed to give you the same sort of data. I'm supposed to give you an element of this applied to 4. And what this means, this plus means, is I'm supposed to either give you this, or this. And depending on which one I give you, if I give you one of these two, then given either true or false, I'm supposed to give you an element of 4. It says, for every element of 4, give me one of these. And whichever one of these I give you me an element of 4. That's what this says. And so this is the data of one of those. So here, the state 1 went to happy, and then true went back to 1, whereas false went to 2. And if you look at 2 over there, state 2 went to sad. And sad says, okay, fine, I need you to, for every true or false, to give me a new element of S. So true went to state 3, and false went to state 2, etc. So the data over there is exactly the data I would need to explain this whole thing to you. This one went to happy again. This one went to dead. And dead did not require me to say any more stuff. Like, there's no thing here that is asking for some element of 4, so I can just stop. Whereas here, there's like a little bit more data. 3 went to, I don't know, 4, and to 1. So this data here is exactly the same as this data here.
So the power is about the number of out edges?
Yep, the power, just like it was here, is the number of out edges. Yep. So that thing there would correspond to, I don't know, it would correspond to, like, maybe I shouldn't do this. Happy, and then there's 2 options, and then either it's sad or it's happy, and then there's 2 options for each of those, and but this one, if it gets true, is happy again. But if it gets false, it's dead. Like, I don't know, you probably can't trace up the tree as what I'm doing, but I'm taking this thing, I'm starting here, and I'm just saying, here's what would happen if you get true, or if you get false, and I wrote down each of those things, and you find that if you did false, true, false. So if you go false, you're sad, you go true, you're happy, you go false again, you're dead. So I could like write that tree out as a kind of infinite fate of what you're going to do given what happens to you. Okay, so p-coalgebras are dynamical systems. And so what I'm going to say next, what are p-coalgebras? Formally, they're this, a set S and a function from S to P of S. But in terms of dynamical systems, they're a set of states, and for every state, for every element of that set, an output, which is one of these coefficients, this, or this. And then for every input there, or for every element of the exponential, a new state. So it's something that outputs something, waits for input, and then moves to a new state. And that's encoded in one of these. You can think of it like a dynamical system, or if you've heard of a Moore machine, it's a Moore machine. Okay, the cofree comonad on P, and I'm denoting it Cp of 1, is a comonad, i.e. is a comonad, and it's given as follows. So you take, so Cp is the limit of y times p of y times p of etc. So you take just y times p of y times p of y times p of y times p of. And you do that forever, and that limit is the cofree comonad on P. And what this is it just like, it's just these infinite trees. It's these infinite trees. And I guess, I don't know. I'm not sure what to say about that. These are infinite trees. Infinite, they're possibly infinite. They don't have to be. Trees. So each node labeled by some element of P of 1 and branching by P bracket I. So for example, someone before asked about, say, 2y. C sub 2y is the set of all trees whose nodes are labeled by elements of this thing of 1. So the nodes are labeled either by 0 or 1. And no matter which one they're labeled by, they branch this many times. So they branch one time, and so they're just bit streams. Whereas like C sub 2y squared would be, well, I don't know why I've started drawing these things horizontally, but 0, 1, these would branch according to 2 every time, and they'd be labeled by either 0 or 1 again. So it's labeled by P of 1, which is 2, and branching according to the exponent there. C sub y, I don't know what else to do. Y squared plus y would be, you have these branches, you're either 0 or 1. If you're 0, you branch, let's say, and if you're 1, you go straight. Let's say that's 0, that's 1, and it's all possible trees you could write that way. So these trees, I guess I should say something else. So, okay, so here's a theorem. So the category of p-coalgebras, so 1 p-coalgebras, these dynamical systems, is the same thing as functors from this thing. This thing, I didn't tell you this. Okay, this thing is always a category because There's a lot I'm skipping over here, and I apologize for that. But C, one of these guys is a comonad, and comonads in Poly are exactly categories. Those are the same. You've heard of categories, probably you know we're talking a lot about categories today. A category is a comonad in Poly. So I told you this is a comonad. I didn't prove it, but now I'm telling you that it is. And so its objects are these like trees. And a morphism from one tree to another is when you take the first tree as like one of these guys, you followed up a finite path, and what you see sitting there is another whole tree. And that whole tree there is the codomain of the map. So comonads in Poly are categories. The cofree comonad is a category. Its objects are the p-trees, and the morphisms are finite paths from one that take one p-tree and find another one in it. And so if you take the functors from this category to set, you get p-coalgebras. And so since this thing is a topos, we found one of our two toposes. So we can study dynamical systems as in terms of topos theory using that, but that's just one element of this theorem here. So Cp of 1 is the terminal p-coalgebra. So these trees form what are called the terminal p-coalgebra. If you do like co-induction or something, these would be what you start with. One thing that's pretty useful is that Cp is isomorphic to y times p of Cp. And a fourth thing, just that Cp is cofree. Okay. Now, why am I saying this? Let's see. We want to study p-coalgebras. These are kind of things like this. And these will be objects in this pre-shoot category or functors category. Cp of 1 is a terminal p-coalgebra, and what we're getting to is that this will be the points of a topological space. So these trees or these streams are the points of a topological space. These streams form the points of a topological space called the Cantor set. But in general, for all of these, we're going to get something called a stone space. And I now remember what I was going to do, which is I'm going to tell you about Cp of 1. This is the formula for that. So Cp of 1 is the limit of a bunch of sets. This is a set, and it's the limit of p compose itself n times of 1, which is trees of height n, all the way down to like p compose itself of 1 to p of 1 to 1. So the limit of this is just saying I don't want just trees of height 1 or height 2 or height 3 or height n. I want infinite trees. And the limit of this is Cp of 1. It's all the infinite trees. And anyone who has studied stone spaces might notice that each of these, if P is finite, each of these is a finite set. And we're getting a limit of finite sets. And that's called a stone space. It's called a profinite set. And that's what we'll be getting to.
Can I quickly start question?
Yeah.
So you wrote C sub P over there to mean the comonad associates with P.
Yep.
A comonad is meant to be a functor in set, right?
Yep.
Where does the input go in the example?
So each of these is a functor.
Right, but so I'm looking at these examples, like C sub 2y to the 1. So presumably I will apply this functor on some x.
Yeah.
Where does x go in those bits?
Right. So these would be like the coefficients. And then x will be for every path, I need you to tell me an element of x.
Okay.
Yeah, sure. Okay, so then there's also the free monad on x, on P. And I'm going to write that as MP. Why did I do that? Sorry. And it's given by, I'm going to assume P is finite here. It's given by the colimit of y plus p composed, y plus p composed of something, y plus p composed something. So just the same as this one, instead of a times, it's a plus, but it's almost exactly the same formula. And so these are finite P trees. Not necessarily, how do you say that? Not necessarily like uniform depth, but each node labeled in the same way and branching in the same way. And I think the camera can't see this, but all I'm writing here is this. Okay, so these are things that look like this. Well, let me just do like m sub 2y squared. It'll be things like 0, and then 1, and then 0, branching, but I'm allowed to stop anytime I want. So that'll be in there. They're not necessarily uniform depth, but that's an element in there. And I don't have time to really go into much now. But p-algebras, in the sense of Lambek, like a set with a map from P of that set to that set, is MP algebras. So this is like, sorry, I'm going too fast. Eilenberg-Moore algebras, and this is like Lambek algebras, if you know what I'm saying. If you don't, it's not really going to come up very much. MP of 0 is the initial algebra. So let's say you wanted the initial algebra on this endofunctor. You would just take this thing and plug 0 in for y. And so much of this would just disappear. Another interesting fact is that MP of x for any set x is isomorphic to MP plus x. You can just put the x in the polynomial and apply it to 0. And that will come up later, except I don't know if we'll have time for the later to come up. MP is isomorphic to y plus p composed MP. And 5, well, MP is free. Is a free monad. Okay. What I wanted to, yeah.
By finitary and lacks important place there.
Yeah, so if P was not finitary, then I need to do something additional to get the free monad. Finitary means that all of my exponentials, yeah, each of these are finite sets. So the branching is finite.
So is there a non-finitary version of this theorem? Or?
Yes, there's a non-finitary version of this theorem. All of these go through, but this one is not true. It's you kind of take the limit of all like finitary projections of your polynomial. You do this to each of those finitary projections, then you just say, oh, throw them all together. And what you get are what are called well-founded trees that say, like, if I only restrict to a finite part of this, I'll see a finite tree, but I make no guarantees if you let me see all the branches. Okay, thanks for the question. So I don't have really much time to say much more because I want to give you guys time for asking questions. But what I want to say is this. So this is the terminal, did I say it? Good. This is the terminal coalgebra, p-coalgebra. It's a limit of 1 from p of 1 from p of 1. Its elements are these infinite trees. Now, each one of these is a set. But a set you can consider as a topological space. It's a discrete topological space, so nothing interesting is happening. And yet, when you take the limit in top of discrete topological spaces, the answer is not discrete. when you take the limit in top, what is the limit in top of a bunch of topological spaces? Its points are the limits of those topological, as the limit of the points. So in other words, a point in this big thing is just, and the limit of these as topological spaces is just one of these infinite trees. But what's weird is the topology. It's not discrete. The requirement is that its projection to each of these pieces should be continuous. And it should be the least thing, have the least open sets, as long as it's got enough such that the pullbacks of these opens are open. So the limit of these topological spaces is the topology on the P trees, like these, where these projections are continuous. And all that's saying is that these projections, like this thing, where it goes on forever, once I just restrict to that part there, that is a finite stage, and whatever I've drawn is going to be open because everything in these finite stages is open. And so this is an open if I consider it as all the branches that go forward from there. So in other words, what it is the open sets of this pro-discrete space. That's what this is called, a projective limit of discrete spaces. An open set of it is just like you pick a finite stage and draw your tree, and you ask for all the trees that truncate to that, and that's open. And all of the opens are the unions of those. So they're just what you can know after a finite amount after a finite time. What can you know? Well, after 10 minutes, I'll know I'm this 0, 1, 1, 0, 0, 1, 1, 1. I don't know what's going to happen after that, but that is an open set. And so the logic of this topos, so this is a topological space, and when P is finite, these are all finite sets, and that's called a stone space. So
are the open sets everything that will truncate to a given tree, or everything that is a truncation of a given tree?
you take any finite stage, you label it, and you look at all the trees that truncate to that,
Okay.
and that's open.
Okay.
Every open is a union of those.
Okay.
Okay, so, right. So I don't really have time to say this, but what I want to say is that CP of 1 are the points of this limit. There's this pro-discrete space. If P is finite, this would be called a stone space. And MP of 1 form a base for the topology. So these guys here, one of these things says, oh, I just don't know what's happening after here. Like, I'm just stopping at some finite stage. Anything that truncates to me is in my open. And every open is a union of one of those. So this is kind of the thing that I thought was kind of neat. P-coalgebras forms a topos. If I think of this thing as like a stone space or just a space, if P is finite, this is called a stone space. If I think of this as a space, then sheaves on SP is another topos. And they're very related. Like this one, the objects of the site, CP, are the points of this topological space. So the objects of this functor of this thing here are the points of this thing here. The free monads involved. It just seems like there's lots and lots of stuff going on. This topos likes to talk about these sorts of things. And when, like, the logic is talking about whenever I receive 2 falses in a row, then I'm going to be sad, or whatever the thing is. This topos is talking about things I can know after a finite amount of time, starting from this moment. So this topos is not allowed to talk about this moment, about the current moment. It's only allowed to talk about whenever statements. This topos is allowed to talk about this moment and all these counterfactuals, like if this happens and if this happens, I can evaluate, like you can evaluate the truth of, like, you can evaluate syntax trees and understand things in kind of a this moment snapshot way. And so there's just some kind of like languagey thing here, or think counterfactuals you can understand after a finite time. versus somehow like experience, where you always move through a single, you're always just moving through experience. You can't go through many paths over here. So I feel like there should be some relationship between these two things. There is a map of monads that takes, like the fact, here's the base for the opens. If I had a map like this that took every open to a subset of points, this is like how I would make such a claim between these two, that every open set in my base gives me a subset of points. I can get this by a map of monads. I'm not going to have time to tell you about it. That I think is also kind of neat. And so there's like all sorts of little connections between these various things I've been talking about, the free monad, the co-free comonad, and these two toposes, and these kind of topologies and stuff. But it's kind of work in progress to understand what this is all really supposed to be. So that's it. Thanks for listening.
Any questions? I'm curious about this monad map and how it relates to the open sets and the points in the space.
Yeah, that monad map. Do you want to see how you derive this from the monad map, or for how you get the monad map? Or derive. Okay. So so MP is a monad. For any comonad and monad, the inner Hom between them is a monad. So, okay, suppose I gave you this map. How could you get the derivation? Well, first I'm going to turn this into MP tensor CP to MP plus 1. Then I'm going to apply 1. But MP plus 1 of 1, over there, number 3 is M of P plus 2, M of P of 2. And so what I want to give you is a map from MP of 2 to 2. Because if I could give you a map from MP of 2 to 2, then I would have a map that takes an open and a point and gives you yes or no. I wish I had this map. But to give a p-algebra on 2 is the same thing as giving a map from P of 2 to 2. Because of this fact. Like, it's enough to give you a map from P of 2 to 2. And for that, what you would do is you basically have in here you have a choice of position, P of 1, of 2 to the P bracket I. And given one of these, given like an I and a bunch of booleans, one for every element of P bracket I just send it to the and over all I and I of BI. And so what this, maybe I should just say quickly what this is doing. You take this monad one that stops after a finite stage, and you take any comonad one of these that goes on forever. And what you do is, if they agree at the first stage, you write it down. If they don't agree, you put false. You use this like little new thing here to say false. So this one and this one agree, so we would draw it. We'd write 0. Then you trace up there and you see a 0. You trace up there and you see a 1. You write false. Over here you see a 0. Dang it, I'm just going to make this a 0. You see a 0 and you write 0. So then you just keep going. So this one stops there. This false is already done. So this and this would go to that. And if you finish this tree out and you never hit any falses, then this and will turn out true. If you hit a false, this and will turn out false. And if you hit a true, this and will turn out true. And what that says is that, like, as long as this one and this one agree the whole way up, it's in the open set. Like, this point is in this open if, when you keep doing this procedure of like seeing if they agree, you never hit any falses. I think it's pretty interesting.
If there are no more questions, we'll stop the recording and thank the speaker again.